Welcome to the deep dive. Today we are focusing on, well, the star that makes pretty much everything possible for us, the sun.
Mm.
It's the engine, right? Providing the essential warmth, the light we need to survive. And of course, that incredible gravity keeps Earth exactly where it needs to be.
Spot on, right in the habitable zone.
Yeah.
But, while that gravity is stabilizing, the sun's influence isn't just light and heat. It's way more complex.
Okay.
We owe it everything, basically. But we also need to respect its volatility. Our sources really emphasize this.
How so?
Well, take the solar wind, that stream of charged particles constantly flowing out. It messes with Earth's magnetic field.
Right. I've heard about that. Solar flares and stuff.
Exactly. Even small shifts in the sun's magnetic field can disturb our own field. And that turbulence, it can send electrical surges right into our communication systems, put stress on power grids. It's powerful stuff.
So this isn't just like basic astronomy. It's really a deep dive into our planetary life support system and its potential dangers, too.
Yeah.
Our mission today, then, is to unpack the sun's entire biography. We're going right back to its birth, 4.6 billion years ago?
Yeah, about that.
Then we'll look at its complex structure now, the physics powering it, and then jump ahead to its, well, spectacular but ultimately final destiny. And ours, I suppose.
It's a huge time scale. So
Mm-hmm.
to make it manageable for you listening, we've broken it down.
Okay.
First, the origin story, how it all formed. Second, its current state, the layers, the fusion engine inside.
Okay.
And finally, its evolution, where it's heading.
All right, let's start with that origin story. We need to rewind way back, 4.6 billion years ago.
Imagine, yeah, one of those spiral arms of our Milky Way galaxy.
There's this enormous cold cloud, a nebula.
Exactly, a giant molecular cloud. And our sources say it was overwhelmingly hydrogen and helium,
Yeah.
leftovers from, previous stars.
So just this huge diffuse cloud hanging out.
Pretty much, yeah. Relatively peaceful, but then something likely disturbed it, maybe a shock wave from a nearby supernova.
Like a cosmic nudge. Sort of, yeah. It introduced an instability. And that caused this giant cloud to start contracting, collapsing inward on itself. Gravity took over.
That collapse sounds simple, but the physics must have been just phenomenal.
Oh, it was everything. Gravity just pulling all that hydrogen and helium into a smaller and smaller space.
It's getting denser and denser.
Right. And as the material fell inward, the atoms started colliding more frequently and, crucially, more violently.
Okay, friction, basically, generating heat.
Immense heat, yeah. The core temperature just started shooting up exponentially. And that rising temperature, that's the key, isn't it, for ignition?
That's the trigger. Once the core hit about, 15 million degrees Celsius?
Wow.
Yeah, the pressure and heat were finally enough to overcome the natural electrical repulsion between the protons, the hydrogen nuclei.
Because they're both positively charged, they normally push each other away.
Exactly. But under these conditions, they could slam together and fuse. Nuclear fusion.
And that releases energy. A lot of energy.
A tremendous amount. It converted a tiny bit of matter into energy, according to Einstein's EMCOA. And boom, the sun ignited. Our star was born.
Incredible. And what's so important for us here on Earth is that the whole solar system wasn't like an afterthought. It formed right alongside the sun, didn't it?
That's absolutely right. The same collapse that formed the sun left behind the swirling disk of leftover material. Gas, plasma, dust.
The leftovers from the nebula.
Yeah, the stuff that didn't fall into the sun itself. Once the sun switched on and started radiating energy, that disk began to cool and organize. Solid bits started clumping together.
Like dust bunnies, but cosmic scale.
Sort of. We call them planetesimals.
Uh-huh.
Tiny building blocks, rocks, and ice.
So these planetesimals, they just started sticking together.
Through collisions, yeah, and their own weak gravity. They accreted, they grew larger and larger, eventually forming the planets we see today.
And the moons?
Same process, really.
Mm-hmm.
Either captured later or formed from the debris around the newly formed planets. It was all one big, messy, integrated event.
Okay, so fast forward 4.6 billion years. Here we are. The sun's a mature star now, sitting comfortably on what astronomers call the main sequence.
Stable hydrogen burning phase.
Right.
Yeah.
But if you could, peel it open like an onion, it's not just a uniform ball of fire, is it? It has layers.
Definitely not uniform. It has distinct layers. 6, actually, that we usually talk about.
6 layers. Okay, let's list them out.
We can group them. 3 inner layers. The core, the radiative zone, and the convection zone.
Got it. Core, radiative, conduction, inside.
And then the outer layers, the atmosphere, the photosphere, the chromosphere, and the really extended corona.
Photosphere, chromosphere, corona. Okay. We absolutely have to start with the core. That's ground zero, right? The engine room.
That's where all the magic happens, the thermonuclear reactions. Every single photon of light starts its journey there.
But didn't you say it's actually quite small compared to the whole sun?
That's the mind-bending part. It only accounts for maybe a quarter of the sun's total radius.
Just a quarter.
Yeah, but because of the unbelievable compression from the outer layers, it contains about half the sun's entire mass.
Half the mass squeezed into a space that's only a quarter of the size. The density must be just insane.
It really is. The sources put it at up to 160 grams per cubic centimeter.
160 grams. What's that like?
Well, for comparison, lead is about 11 grams per cubic centimeter. Gold is around 19, so this is roughly 8 times denser than solid gold.
Wow. Okay. And it's all plasma, right? Super hot, super dense plasma.
Exactly. Held together by the sun's own immense gravity.
All right, so energy is born in this crazy dense core. How does it get out? It's got a long way to go.
It does. First, it has to travel through the radiative zone, and this zone is huge. It takes up most of the sun's volume.
Radiative zone. So energy moves by radiation.
Primarily, yes. The plasma here is still incredibly hot and dense, so photons, particles of light, energy, they don't just stream outwards. They get absorbed by an atom, then re-emitted in a random direction, travel a tiny distance, get absorbed again.
Like a drunken walk outwards.
Huh? That's a pretty good analogy, actually. It's called a random walk. It's a very slow, laborious process. Radiation is how the energy slowly percolates outward.
I heard somewhere it can take like hundreds of thousands of years for one photon to get through just the radiative zone. Is that right?
That's the kind of time scale estimates suggest, yeah. Could be even longer. It's staggering.
Okay, so after this epic journey, it finally hits the next layer.
Right, the convection zone. This is the outermost internal layer. Here, the plasma is a bit cooler, less dense, and it becomes unstable.
Unstable how?
It starts to behave like a giant pot of boiling water. Hot blobs of plasma rise rapidly towards the surface because they're less dense.
Convection currents.
Exactly. They reach the surface, radiate their heat away as light, cool down, become denser, and then sink back down to get reheated. Giant churning convective cells.
And that's what brings the heat to the actual surface we see.
That's the final step, yeah. It efficiently transports the energy through that last internal layer to the photosphere, which is the visible surface.
That whole cycle is just incredible. But let's jump back to the core for a second. Fusion. You hear about it as this ultimate energy source, but it's famously difficult to achieve here on Earth.
Extremely difficult.
So how does the sun make it look so easy? The sources mentioned 3 key requirements it meets perfectly.
Right. It nails all 3. First, as we said, temperature. You need that extreme heat, 15 million degrees Celsius, to give the hydrogen nuclei, the protons, enough kinetic energy.
Energy of motion.
Right. Enough speed to overcome their mutual electrical repulsion. Remember, positive charges repel each other. You need to slam them together hard.
Okay, high speed overcomes repulsion. Got it. What's number 2?
High density. You can have high temperatures, but if the particles are too spread out, they just won't collide often enough to sustain the reaction.
You need lots of chances for collisions.
Exactly. The core's incredible density ensures a high rate of collisions, making the fusion process efficient and continuous.
Makes sense. And the third requirement, something about containment.
Yes, a suitable containment vessel. This is the huge challenge for fusion power on Earth. How do you hold on to plasma that's millions of degrees hot?
Material walls would just vaporize.
Instantly. We use complex magnetic fields, magnetic bottles, but the sun, it has the ultimate container, its own gravity.
Gravity itself holds it all together.
The immense pressure from the overlying layers just contains the core, preventing the reacting material from expanding or, touching anything inappropriate. It's self-contained.
So the core is this perfect storm of gravity, density, and heat, creating this ongoing, stable nuclear reaction for billions of years.
Pretty much, yeah. It's been steadily burning hydrogen for about 4.6 billion years.
Okay, so we understand what it is, how it works inside, but how do we even know all this? How do we measure this thing? It's huge, it's powerful, and it's really far away.
Well, the fundamental distance, the sun's distance from Earth, is key. We define that as 1 astronomical unit, or AU.
Right, about 150 million kilometers or 93 million miles.
Roughly, yeah. That AU is like our yardstick for the solar system.
Yeah. I just want to clarify something. The sources mentioned kiloparsecs earlier when talking about distance. That's not the sun's distance, right?
Oh, good catch. A kiloparsec is a unit for much, much larger distances, interstellar galactic distances. Thousands of light years. The sun is just 1 AU away from us.
Okay, thanks. So 1 AU. How do we nail down that number? And how do we measure other things, like its size or energy?
It involves some really clever physics and careful observation. One classic method is parallax.
Parallax. Isn't that about how things seem to shift position when you look at them from different angles?
Exactly. We observe the sun, or rather nearby stars relative to very distant background stars, from two different points in Earth's orbit, say in January and then 6 months later in July.
So we use the diameter of Earth's orbit as a baseline.
Precisely. We measure the tiny apparent shift in the star's position against the background, that's the parallax angle. Knowing that angle and the baseline distance, Earth's orbit diameter, basic trigonometry gives you the distance to the star.
But wait, you need to know the size of Earth's orbit to use parallax. How do we know that distance accurately without already knowing the distance to the sun? Sounds a bit circular.
Ah, that's where another genius piece of physics comes in. Kepler's third law of planetary motion.
Kepler. Okay, what does his law tell us?
What's amazing is you don't need the distance to start, you just need time. Kepler's third law relates a planet's orbital period, the time it takes to go around the sun once.
Which is 1 year for Earth. We can measure that very accurately.
Exactly, t, the period. The law states that the square of the orbital period, t1 square, is proportional to the cube of the average radius of its orbit.
T squared equals
I
some
thought-
constant times r cubed.
Essentially, yes. The full form involves the sun's mass
Yeah.
and the gravitational constant g. It's 2 days, 4 pi 2 gm, r33. Since we can measure t very precisely, and we can determine the sun's mass through other gravitational effects,
We can calculate r, the radius of Earth's orbit, the AU.
we can calculate the ratio and then use other methods like radar ranging to Venus to calibrate the actual value of the AU. But Kepler gives us the scale of the solar system just from timing the planets. It's incredibly powerful.
That really is clever. Okay, so we can measure distance. What about the sun's energy output? Its power.
For that, we use other fundamental laws, like the Stefan-Boltzmann law.
Stefan Boltzmann, right.
It connects the sun's total energy output per second, its luminosity, L, to its surface temperature, T, and its surface area, A. The law is law dollar equals sigma, a key 43, where sigma is a constant.
So if we know its temperature and size, we know its total power output.
Exactly. It tells us how much energy is pouring out based on how hot and how big it is.
And temperature. How do we measure the temperature of something we can't touch?
That's where Wien's law comes in.
Wien's law. Okay, this one always seemed a bit abstract. What's the core idea?
Wien's law connects the temperature of an object that glows due to heat, like a star,
What?
to the color of light, or more precisely, the wavelength of light where it emits its peak energy.
So hotter things glow bluer, cooler things glow redder.
That's the gist of it, yes. The law, and the Max constant, tells us that the peak wavelength is inversely proportional to the temperature, T. For the sun, the peak emission is in the yellow-green part of the spectrum.
Which tells us its surface temperature is around 5,500 degrees Celsius or so.
Exactly. Wien's law lets us take the sun's temperature just by looking at its color.
Amazing. Speaking of light and color, let's really focus on the solar spectrum. The sources called it a fingerprint.
It really is. You spread the sun's light out into a rainbow, a spectrum using something like a prism or a diffraction grating. You see the familiar colors, red around 700 nanometers wavelength, down to blue and violet around 400 nanometers.
But it's not a perfectly smooth rainbow, is it?
Not at all. When you look closely with good instruments, you see thousands of thin, dark lines crossing the spectrum. These are called absorption lines. Fraunhofer lines, technically.
Absorption lines, meaning something is absorbing light at those specific colors.
Precisely. As the continuous rainbow of light generated deeper inside travels outwards through the sun's cooler outer atmosphere, the photosphere and chromosphere.
The atoms in that atmosphere absorb certain frequencies.
Exactly. Each chemical element, hydrogen, helium, iron, calcium, whatever, absorbs light only at its own unique, specific set of frequencies or wavelengths. It's like they have barcode patterns.
So those dark lines are like missing colors, stolen by the atoms.
That's a good way to put it. They create a pattern of dark lines that acts as a unique chemical fingerprint. By matching the pattern of lines, we see to the known patterns for different elements measured in labs.
We can tell exactly what the sun's atmosphere is made of.
Bingo. That's how we know the sun is mostly hydrogen, about 74%, and helium, about 24%, with small traces of other elements. We can analyze the chemical composition of a star 150 million kilometers away just by decoding these dark lines. Instruments like the McMath Pierce Solar Telescope were crucial for this.
The power of spectroscopy, it's just incredible. Okay, we know how it formed, how it works now, how we measure it, but now we have to look ahead to the sun's future, its evolution, and, well, our ultimate fate.
Right. The sun won't stay on the main sequence forever. Stars evolve as they burn through their fuel. We can track this on the Hertzsprung-Russell, or HR, diagram.
The HR diagram plots stars based on luminosity and temperature, right?
Correct. And stars move around on it as they age. The sun is currently stable, fusing hydrogen in its core. But eventually, that core hydrogen will run out.
And that's when things get dramatic.
That's the first major transition. When core hydrogen fusion stops, the core contracts under gravity and heats up. This intense heat ignites hydrogen fusion in a shell around the now inert helium core.
So fusion moves outwards?
Yes. And this shell fusion is actually much more intense than the core fusion was. It generates a huge amount of outward pressure, causing the sun's outer layers to swell up enormously.
It gets bigger, much bigger.
Massively bigger. Its surface area increases immensely, but because the energy is spread over such a larger area, the surface temperature actually drops slightly. It becomes cooler and redder. This is the red giant phase.
A red giant star. Okay. And that phase doesn't last forever either, does it?
No. As the core continues to contract and heat up from the shell burning, it eventually gets hot enough, maybe 100 million degrees, to start fusing the helium that's accumulated there into carbon.
So a new fuel source kicks in. Helium fusion?
Right. The star might shrink and heat up a bit during this phase, but helium doesn't last nearly as long as hydrogen. Once the helium fuel in the core is exhausted, fusion reactions pretty much sputter out for a star of the sun's mass.
And then what?
The star becomes unstable again. It puffs off its outer layers into space, creating a beautiful structure called the planetary nebula,
Leaving behind just the core.
leaving behind the incredibly hot, dense, dead core, made mostly of carbon and oxygen. This is a white dwarf star. It's tiny, maybe the size of Earth, very dense and very hot initially, but it just cools down slowly over billions of years because there's no more fusion-generating heat.
Okay, red giant, then planetary nebula, then white dwarf. That's the sun's future path. Let's zoom in on that red giant phase, though. That sounds like bad news for Earth.
It is. The 2008 astrophysical model we looked at gives some pretty specific details. As the sun becomes a red giant, it's expected to expand out to maybe 250 times its current radius.
250 times. That would definitely engulf Mercury and Venus. What about Earth?
Well, there's a complication. As it expands, the sun also loses a significant chunk of its mass, maybe about 33% through a stronger solar wind.
Less mass means less gravity. Does that help us?
Initially, it seems like it might. Less solar mass means Earth's orbit should naturally widen. The model suggests our orbital radius might increase by about 50%, maybe out to 1.5 AU. That sounds like it could put us just outside the sun's expanded edge. An escape, maybe?
Okay, there's a glimmer of hope, but I sense a but coming.
There's a big but. Tidal forces.
Tidal forces, like the moon causes tides on Earth.
Similar principle, but much, much stronger. As the sun bloats into a red giant, its rotation will slow down dramatically. You have this huge, slow-rotating extended star. It exerts immense tidal forces on nearby Earth.
And what does that do?
It creates a bulge on Earth facing the sun, and the sun's gravity pulls on that bulge. But because the sun is rotating slower than Earth orbits, this tidal interaction effectively acts as a drag force. It pulls Earth inward.
So the orbit tries to widen because the sun loses mass, but the tidal drag pulls us back in. Which one wins?
According to the model, the tidal drag wins. It counteracts the orbital expansion and then some. The Earth gets pulled closer and closer to the expanding sun.
No escape then.
No escape. The model predicts that Earth, along with Mercury and Venus, will inevitably be engulfed by the expanding red giant sun.
Wow. When is this predicted to happen?
The estimate is about 7.59 billion years from now, give or take.
7.59 billion years. And the model actually pinpointed something even more specific, didn't it? About the timing relative to the sun's maximum size.
Yeah, it suggests engulfment happens about 500,000 years before the sun reaches its absolute maximum radius in the red giant phase.
500,000 years before the peak. And here's the detail that just gets me. The margin is so small.
It's incredibly tight. The calculation suggests that if Earth's current orbit were just 0.15 AU larger, so if we started at 1.15 AU instead of 1 AU,
Just 15% farther out.
yeah, roughly 22.5 million kilometers farther out, then the orbital expansion due to mass loss might just barely win out over the tidal drag, or Earth could potentially survive just skirting the edge.
That's maddeningly close. A cosmic near miss determined billions of years in advance.
It really highlights how finely balanced these orbital dynamics are.
So what happens once Earth is engulfed? It's not instant annihilation, is it?
No, it's a process. Earth would first pass into the sun's incredibly tenuous outer atmosphere, the corona, then into denser layers. It would experience intense atmospheric drag, like a meteor hitting the air, but much worse.
Bombarded by plasma.
Exactly. That drag would cause its orbit to decay very rapidly, spiraling inwards until it eventually plunges into the sun's much hotter, denser interior regions. And that would be that.
A fiery end. But what about the rest of the solar system? Does anything survive?
Actually, yes. The model suggests only the three inner rocky planets, Mercury, Venus, Earth, get swallowed.
Yeah.
Mars might just survive, though it would be scorched.
And the outer planets? Jupiter, Saturn.
They should be fine. In fact, their orbits will also expand due to the sun's mass loss. And here's a fascinating twist. The habitable zone, the region where liquid water could exist, will shift dramatically outwards.
Outwards, beyond Mars.
Way beyond Mars.
Right.
During the red giant phase, and even later as the white dwarf cools, the habitable zone could temporarily encompass the orbits of Jupiter and Saturn, maybe even Uranus and Neptune.
So, moons like Europa or Titan could potentially have liquid water on their surfaces for a time.
It's a possibility, yes. Liquid water could exist far, far out, well beyond Pluto's current orbit, for potentially millions or even billions of years during the sun's final stages. A whole new potential zone for life, long after Earth is gone.
A solar system-wide migration of the life zone. That's quite a perspective shift.
It really is.
Okay, that's an immense journey we've taken. From that initial nebula collapse, through the physics of the core,
The high density, the extreme heat needed for fusion.
using incredible tools like Kepler's laws, Wien's law, spectroscopy to understand it from afar,
Right, decoding those dark lines in the spectrum.
all the way to its ultimate evolution into a red giant,
Oh,
and
see.
the unavoidable fate of the inner planets due to those tidal forces.
When you step back, perhaps the most powerful takeaway for you listening is how we can piece together this entire life story, past, present, future, of an object 150 million kilometers away, mostly just by carefully analyzing the light it sends us.
That fingerprint in the spectrum?
Exactly. Those dark lines tell us its composition, which confirms how it works now and allows us to predict its future based on well-understood stellar physics. It makes something incredibly distant feel tangible.
So maybe a final thought for everyone to consider. We talked about that incredibly narrow margin, just 0.15 AU, that separates Earth's engulfment from potential survival. It really drives home the immense, almost subtle power of fundamental forces like gravity and tidal interactions. They operate over billions of years, shaping destinies on a planetary scale. What other seemingly small details or universal laws might be quietly steering futures we haven't even begun to calculate yet? Something to think about.